All right, I subtitled this Why I Still Use TF-IDF in 2026. Quick show of hands, who's familiar with TF-IDF? Sweet, that makes me really excited. Okay, great, that means you have no idea what I'm talking about. So, I honestly thought I was gonna come in here and I was gonna be like talking to a Tesla convention about carburetors. So, you make me feel a little bit better. Just a real quick introduction, tell you a little bit about who I am. My name is Chris Taylor. I am lead data scientist at American National here in Springfield. I lead a team of data scientists as we try to get the organization to be more data-driven in how they make decisions. I grew up in Poplar Bluff, Missouri, which is just above the Boot Heel, home of the mules. That is one great looking mule. I grew up on a sheep farm, so I'm an ex-shepherd. My dad looked at me one day and he said, "Son, this is the best life I can offer you unless you get an education." So I got really educated. I have a PhD from the University of Kansas in data science. However, more people know me as Springfield Thor than know me as Dr. Taylor. Springfield Thor has made numerous charity appearances, visits kids in the hospital, has raised thousands of dollars for local charities. That's actually how I met my wife, was at a charity event when I was Thor. And we recently hosted a Renaissance-themed wedding, which we thought was super awesome and cool. We had axe throwing and a whole bunch of other fun things. And our lovely cat, Poozy, who is Darwin makes us a family of 3. And, little known fact, I was on Wheel of Fortune back in 2006, won $8,600 in cash. So that was kind of cool. I did not make it to the bonus round. That was something. I've written a few articles out there. I've got a chapter in a textbook on the problems in bioinformatics. So just a little bit about my background before we get into the fun stuff. So I already mentioned some of my trepidation about coming in and talking about an ancient technology. And TF-IDF and I are the same age. It was first introduced in 1972. And I had a conversation with ChatGPT, like, am I coming in here talking about something really stupid that these people are like, why, we don't care? And I asked it just, what's something I can put up on the screen while I'm talking about it? And it came up with this image for me. And I couldn't have been more perfect. All right, I do believe TF-IDF is super useful. I'm going to explain why I prefer it over embeddings, how to implement it. I'm going to give you all the math. That is crazy easy. You can do this without any token counts. So here's my use case. I work for an insurance company. We want to be able to streamline insurance claims, but however, you have to have somebody read it and go, what type of claim is this? Was this a collision? Did they hit a deer? Did the house burn down? What happened? We found a way to do it without a person. So here's how we did it. First, let me talk a little bit about the differences between TF-IDF and embeddings. TF-IDF is easy to explain. I'm going to explain all the math to you, and you're going to see why it always gives you consistent results every time, and you know why it gave you those results. So it's not a black box. You know exactly why it's giving you what it's giving you. It's crazy fast, not only to develop, but when it runs and executes. It's cheap. You don't need a GPU to run it. You can run it on a local box, and it's fast. However, it has problems in finding semantically similar concepts, and it doesn't handle synonyms. Let me show you what I mean. For example, it does not understand the difference that a vehicle and an automobile and an IV, insurance term stands for insured vehicle, are all the same thing. TF-IDF does not know that. If there are typos in words, it will treat them as different words. So it has limitations. Similarly, it doesn't understand context. So when it sees Apple release quarterly earnings and apple pie recipe, those two apples are the same to TF-IDF. And lastly, it doesn't understand intent. So if somebody says, I want to cancel my policy or I want to terminate coverage, it's going to treat those as two totally separate things because it doesn't understand the meaning. It's just a statistical engine. All right. So I'm going to start with a very oversimplified example to walk you through the math and explain how it all works, because I think it's wicked useful. And then we're going to end with a bigger use case, what I've done with it, and then talk a little bit about how we can use LLMs to help us create classifications. So it's super convenient when you have pre-classified data. In this case, I have a bunch of free text descriptions of claims. That whoever took the call, whether it was the agent, whoever reported it, this is how they described it and typed it into our claim system. Then a person looked at it and they said, oh, that was fire. Oh, that was collision. Oh, that was they hit a deer. So I've got this pre-classified data classified by a person. I'm basically capitalizing on their expertise to create a model. So in this example, we're going to talk first about the TF in TF-IDF, which is term frequency. In this case, little background on TF-IDF, it's the origins of search engines. In fact, it's still this kind of what drives them underneath the hood. They've gotten a lot more sophisticated, but this is still kind of how they work. In this case, the term frequency is the number of times that word occurs in a document. In this case, I'm going to use how many times does that word appear for a particular claim type. So in this case, I've got two claim types, fire and hail. And I have two claims, so you can see the text here. All right, the first, battery started fire in garage, doing damage to the garage. It's 10 words. So you're going to see off to the right, I created term frequencies for them. Garage appears twice in that description, so it's 2 out of 10. That's its term frequency. So if I'm going to do this on a large body of information where I have a whole bunch of different claims that are fire, I just aggregate all the words together, concatenate them, count how many they are, and then create term frequencies for each word that appears in that category. Everybody with me so far? All right, cool. I told you this is easy. All right, the second one is hail. Hail damage to exterior of home and pool. So there's only 8 terms in this one, so and none of them repeat. So each of them's got 0.125 term frequency. Now, what you really should do, and I didn't, because I want to give you a very easy to follow example, words like in, to, the, doing, don't provide meaning. Throw them out. So identify those words up front, throw them out. They don't give you any useful context. Nobody searches for the word doing. So throw it out. Don't have it in your dictionary. Save space. Okay, so this is term frequency. Very easy. Let's talk about inverse document frequency. This is basically how well does this word help me classify across different types or across different documents. So yeah, this is just my dictionary. I'm getting ahead of myself. This is my term frequency dictionary. All the words and their frequency for each particular type. You're going to see damage is the only one that crosses. Damage appears in fire claims and hail claims with different term frequencies for each. All right, now we get into the inverse document frequency. This fancy math at the top, the N is just the number of classifications you've got, the number of categories, the number of documents, the number of buckets you've got is N. The one underneath it is how many different buckets this word appears in. So for example, the word garage appeared in one of my 2 buckets. So 2 divided by 1 is 1. The log of 1 is 0.3. A little over, but yeah. So that's it. All right. So you saw earlier that the word garage appeared in both. 2 divided by 2 is 0. Log of 0 is, sorry, it's 1. 2 divided by 2 is 1. Log of 1 is 0. It means that word has no usefulness in telling me which one this really is. With me so far? All right, great. Thank you for nodding. That really helps me. Okay, so now this is what my entire dictionary looks like. For every term that I have seen anywhere, I have a term frequency for each bucket that I want to put it in, and I have an inverse document frequency for each word. Now, this is an oversimplified example. There's only 2 examples. So term frequency for the IDF for everything is 0.3, except damage, because it occurs in both. So it has no useful information for it. Okay. Let's try a new thing. This is a new claim we haven't seen before. And we want to determine which bucket does this go in. We're going to use that dictionary to figure this out. Storm caused exterior damage to garage and home. All right, first word, storm. We have never seen that word before. It's not in our dictionary. It has a value of 0. We don't know what to do with it. Same for cause. Exterior, however, We've seen this one before, but not in fire. So you can see 0, because that's the term frequency in fire, times 0.3, the inverse document frequency. 0 times 0.3 is 0. However, exterior under hail, you see it's 0.125, because it's one of the 8 words that we saw, times 0.3. So there's a 0.038 next to hail. You do this for every term, and then add them up. Whichever gets the biggest number wins. It's very easy to check your math and see, why did this one go into that bucket? Very easy to trace. I know exactly why the classifier is making decisions it does. I can't do that with Claude. But here I know exactly why it's making the decisions it's making, and I can modify it. So one of the things I like to do personally is I put in a 0-term penalty. So for each word that returns a 0, I subtract from that total count. And I found that gives me really good results. Okay, so this is a very simple example for TF-IDF. Let's expand it. For this particular use case, I took 5 years of claim data, 484,000 unique claims, and all of their little short descriptions, and did exactly what I just showed you. 76 buckets to put them in. And some of these buckets are stupid similar, which makes it that much harder. Yeah, exactly. Exactly. Okay, so here we go. This is what it looks like. There were 44,000, almost 46 unique terms in the dictionary. And as I mentioned, I dropped stop words like the, and, or, the useless words. And I just took a snapshot here. Across the columns across the top, you can see the cause of loss, the different buckets that I'm putting claims in. Underneath each one, you can see the term frequency for that word in that bucket. And on the far right, you see the inverse document frequency, which is basically how valuable is this word in helping me distinguish between different buckets. So I'm going to point out the highest one is poisonous. It only appears in one claim, and it's livestock. Okay, that makes sense to me. And it's got the highest term frequency. So when I see the word poisonous, I know what kind of claim that is. It's livestock. And I'm doing this all without token counts, and it's trained on data that I've already got. Okay. I don't know. Oh, yeah, I threw in the most useless term was the word insured. And just for giggles, I thought I'd throw in the most predictive term for each claim type. So for claims, cause of loss, collision with animal or bird, the word deer was the most predictive of that. These are going to be like duh things, but it's one of the reasons I like TF-IDF. Glass breakage, rock, wind, roof, theft, stolen, flood, water, hail. And for towing and labor, the word was tow. So again, it adds that confidence for me. I know what it's doing, I know why it's doing it, I feel really good that this classifier is going to do what I want. By the way, I didn't time this presentation, so I have no idea how long we're going to go, but I think we're about halfway through. So this may end up being really short. But we'll see when we get to questions. Okay, so for testing, I used a k-fold cross-validation. I don't know why I picked 7. Most of the time people pick 10, that's what you usually see in the literature. I don't know why I picked 7. In case you're not familiar with k-fold cross-validation, I trained my model on the entire data set. Okay, well now I don't have testing data. So I'm going to leave 1/7 of the testing data out and pretend I've never seen it before and train on the other 6/7 of it. Okay, so now I've got training data and now I have testing data that I'm pretending I don't know the answers because the model hasn't been trained on it. You do this 7 times, each time leaving out a different 7th. Okay, and then you average the results. It's a nice technique for determining your accuracy, especially if you don't have great testing data. Like, hey, let's just take data we already know the answer for, set it aside and don't train on it. I have a feeling this is like going to be the biggest takeaway from the entire presentation, is this slide. So anyway, we did this. and I matched, my little model matched the cause of loss determined by a human in our claim system 83% of the time. All right, here's one of the things I find fascinating. Ask somebody like, hey, we want to have an AI classifier. How accurate do we need it to be? Everybody's like 95%, 99%. Like, your people aren't that good. So I tested it with the people. I actually had an actual claims adjuster review some of my results. I picked out 25 where the claims record and the model agreed. They said the same cause of loss. The adjuster agreed with it 88% of the time. That tells me something about the data I'm working with. So even the data I trained on has issues because, you know, it's classified by people. And if you want 90% accuracy, I can tell them, I can't get you 90%. Your people aren't even 90%. Okay, so they had another 49 where the model and what was on record disagreed. The adjuster agreed with the claims record over my classifier 15% of the time, 7 of those 49. They agreed with my model 85% of the time over what was on record. That made me really happy. And here's the other thing that I'm most proud of. 33 of those 49, the human classified it as other. The model gave it an actual description. That was awesome. One of the other things that we can do with this is in insurance companies have insurance. It's called reinsurance. And they're basically like, hey, there's only so much risk we're willing to take, so we want you to share part of this risk, and we'll pay you to take some of that off our hands. So like if there's a big storm that causes a few $100 million in damage. There was a giant hailstorm in South Dakota a couple of years ago that was devastating. So you offload some of that with the reinsurance company, and then when you have claims come in, you're like, hey, I want to file a claim with you for these claims. Okay, I mention all that because the cause of loss matters in that situation. So when there was a lightning storm that caused a lot of fires, there's 2 causes of losses in there. One is lightning and one is fire. We were submitting claims for reinsurance for the ones that said fire. But if the human adjuster called it, sorry, other way around, for lightning, we were submitting reinsurance claims for lightning, getting reimbursed. But when we did a query in the system, we only looked for lightning cause of loss. There were several cases where a human said the cause of loss is fire because it got struck by lightning and burned down. We didn't get reimbursed for those. And this model caught them to the tune of several $1 million that we could get back. Oh, and then the last little bit. Of the 16 non-other mismatches, the adjuster agreed with the model 70% of the time. So the model's doing all right. We can probably make it better, fine-tune it a bit, and one would be like get rid of some of those redundant categories. There's one for fire, and there's one for fire/heat. Okay, so everything I've talked about so far is I've got this nice data that's already trained. What if you don't have that? Nobody wants to read through hundreds or thousands or hundreds of thousands of text records and say, oh, that goes in this one, that goes in this one. How do you address that? Oh, that's where the LLMs come in. So I iterate with an LLM. I run each of my training examples through, and here's a prompt that I use. You're an AI designed specifically to assist humans in categorizing free text descriptions of automobile claims. You provide short summaries of claim descriptions to help humans quickly identify the reason for the loss. Give a short, 1 to 3 words summary of the claim description. And then I fed each one through. That was actually GPT 3.5 because token cost was cheap. And then it will spit out basically categories. Those 1 to 3 words become your categories, and they don't match. Because it'll give you a different answer at a different time. So consolidate them. Decide what you want the categories to be based on these suggestions you get back from the LLM. Then you decide on the categories. It's done a lot of the heavy lifting for you, which is what I did. consolidate the categories down, and then you prompt again. This time you pass the categories you picked as part of the prompt. You're like, hey, I need you to classify this. These are the acceptable categories for you to choose from. And it classifies your training data for you. Now, it's not going to be 100% accurate, but neither are people. So it's good enough. Okay, and then once you've got that, you build your TF-IDF model using the data that your LLM has classified for you. And that looks like this. So you can see off to the right, you can see road debris, tree damage, road debris, chip repair, backing accident. Look at, they're consistent. Because I told it these are the only ones you can pick from. And this worked out really, really well for me. I was able to build a TF-IDF model off of this and do classifications on it. It's a different type of auto claim. These are business auto policies. I'm going to pause just so you can read some of them. Some of them are crazy. Oh, OV, I told you, is insured vehicle. OV is the other vehicle. Yeah.
Unknown person stolen
Yeah, it's like that. All right.
The XY have it, or did he have the XY?
I don't remember. And I actually had some examples that I was going to bring in. I deleted those slides, but they were descriptions of actual claims. And I'm like, these are great. And one of them, it sounded like a theft, and my mom was like, nope, they just lost it. And it turns out they had just lost it. They found it later, withdrew the claim. Yes. Okay, so this is the prompt that I used where I actually pass categories. So I use a system prompt, like a chat. Use a system prompt, specify these specific categories, and like, hey, I want you to pass your answer in a JSON, format, and I get back really nicely formatted results that they're all categorized now. That's it. That was crazy fast. Okay, I was supposed to wait till the end for questions.
Any questions? I'll bring the mic to you.
To what extent does the initial classification of the data affect the output of the IDF model? And is there any way to increase the accuracy of the output of the IDF model without increasing the accuracy of the training data? So like if I had a bunch of blind monkeys to my data, is there any way I can get something still usable?
That's a great question, and I think I understand what you're saying. Let me repeat it back to you, my understanding, make sure I'm on the same page. So if we have really badly pre-classified data, can we improve that? That's where I would suggest feeding it through a large language model and seeing what it can do with it, and then build your TF-IDF off of that. You can also, and this is what my team did, so they took my TF-IDF classifier and then ran it with some other things, with some random forests and some other things, and made this hybrid model that outperformed my initial classifier. So yeah, it's always good to have a team look at your work as well, and they'll say, yeah, this is cute, old man, we can make it better. It's a good question.
All right. Essentially, my question revolves around the similar thing to yours. You early on in the presentation said, oh, we can't have LLMs classifying all this. They'll do a terrible job. If they want super high capability, we can't give that to them. And then later on, you're like, well, but the LLMs are useful for some classification. And in your response, you just outlined you think that LLMs are better than humans. What happens when there's a situation where the LLMs, in whatever way that they do, have somehow mucked with your training data in a way that you can't necessarily find, because they are black boxed and you can't figure out what they have done, and reverse engineering that is going to be a heck of a challenge. What do you do when the LLM becomes the bottleneck for your data purity?
Oh man, that's an exceptional question. I believe, and I like the fact that TF-IDF is open. So I can start looking at the specific words and going, why is it putting it in that category? Why does it think that's where it goes? And then I can start breaking it down and looking at specific training examples. And I've done that exact thing. Looking at specific training examples and go, oh, it's putting it in this category. That's not where I want it. And then I can either reclassify that specific training example, or I can do like, you know, the zero penalty I mentioned. That also helps with some of that. So if you've got one word in a search that's really outweighing everything else in the search, penalizing those zeros can balance that equation and make it better and more accurate. Really good question. I feel like I gave a lame answer, but thank you.
Why is virus 100% correlated with theft?
I don't know. I want to look at that though. That's funny.
So you were saying at the very beginning that it can't differentiate between different terms meaning the same thing. If you wanted to take the time, could you come up with a like if this.
Yep.
And have you done that?
Yes. So there's two good strategies for that. One is the thesaurus, where you just start equating terms, and then what you do is you just replace terms. So if you see this word, always replace it with this word. And that helps with that. Another strategy is called stemming. So like swim, swimming, we know those are the same thing. TF-IDF does not. So replacing those stem words, run, ran, those kinds of things,
Yeah.
similar idea. You want to look at all the different stems of a word and then just replace them all. And that makes life a whole lot easier. Yeah, another great question.
So when you're using the LLMs to classify stuff, how often did you need to rewrite your prompt to account for some of the times where you send the same data in and get different data out just because it's an LLM?
So that's why, so the first pass, where I send all the descriptions through and it gives me categories, I took all those categories out and I dropped them in Excel and made just a unique list. And then I picked the ones I liked.
And then you went back and
And then I reclassified
it.
it, yes. And then I did that exact thing in the training data, so it's like road debris. There's another one that was like thrown rock. Those are the same. So I picked road debris, and then where it said thrown rock, I replaced it with road debris, and there's my training data.
What's the situation where, like with the stolen thing that you mentioned, where the system ended up coming up with an unorthodox solution that ended up being correct? What's a situation like that happened on a grander scale, where it started correlating a specific word, you're like, that doesn't make any sense. But then it started being right, and you're saying, well, that doesn't, well, I guess it does make sense.
Yeah, I don't have any good examples of that. The one that popped into my head was the example I gave you of somebody reported some stolen jewelry, and the classifier like, it's not stolen, they lost it. And they found it later. That was my favorite example of where I have seen that. There may be other examples, I just didn't pay attention. Because, there's almost 500,000 of these. Back.
So do you have users review the suggested answers as they go? And if you do you keep feeding that new input that's coming into the models to keep evolving it as you go?
That's the ideal way to do it. It's like, that's the peak. What I ran into and why I resorted to the LLM was the experts that I needed to classify. I'm like, how many do you need? 50? Like, no. I need a few thousand to train on. And like, I'm not rating 1,000 of these. Which is why I ended up going with the LLM. Because what you described is the perfect example of, I want somebody to go through all of these, make sure the training data is good, and I couldn't get anybody enough time for people to go through it, and nobody wanted to spend their time doing that. Which is why I think the LLM becomes your best friend.
These are great questions. Any more? I want to bring Oh, sorry, I'll come back over you.
To piggyback on the last question, if you were to have more documents to train on, right, is there a technique you can use to train on the additional data without retraining on the whole corpus of data?
Yes, absolutely, yes.
What is that called, roughly? Do you know offhand? It's okay if you don't,
I don't have a name for it. I just like, here's a new word I've never seen before, add it to the dictionary.
There is a way to do that.
Yeah, compute the, the IDF for it, and then I gotta modify term frequencies, because now there's an extra word in there. But outside of that, that's the update.
So, do we think like the LLM gonna be smart enough to identify any spelling mistakes on the words? Like if there are any cut off words, like the spaces between the words, is it smart enough to identify those and give the results for us, or it's gonna just ignore, or it just is just an idea?
I think that's another area where LLMs really, really help in classifying data. So just for example, you'd be surprised at the number of different ways someone can spell Corolla. And all of them show up in my dictionary. Every misspelling shows up in my dictionary. Where, and I know they can correct spelling because Grok does it to me all the time. It's like, I think you meant, and it gives me the whatever term or correct spelling I was trying to use. So yeah, they can totally help with that. And another reason why I encourage it, because people are on the, where I got my claims descriptions, it's somebody on the phone with the client, typing in as the person's talking, and sometimes they don't even understand what the person meant. They just type it out phonetically what they think it was. And so you've got all these weird terms that show up in the data. So yeah, it's another way, like LLMs help me to classify my data, yeah. So, and just to circle back to my dinosaur photo in the beginning, I'm not trying to come in here and like, stop using LLMs, TF-IDF is better, and it's older. That was never my intent. I just found it really useful. And I like the fact that I can see why it's doing what it's doing, and I can edit it. So if I don't like the results I'm getting, I can modify it. And as I mentioned before, embeddings they definitely have superiorities over TF-IDF, which is why I like a hybrid combination of the two, running my training data through an LLM, fix those misspellings, catch all those things in there, help me classify this data that no human wants to read and come up with descriptions for. Yeah, there's one. If you don't already have categories, ask people to try and come up with categories for you. That's horrible. And always there's an other category. Like, no! That's like the junk drawer at home. That's just where everything goes and nobody starts reading anything anymore. No, thanks for all the questions. Oh, we got one more.
Yeah, do you have any plans or have you tried yet comparing your IDF model to an LLM provided with the same limited set of categories and seeing how the accuracy compares? So your layered approach versus just the LLM approach, and then compare to whomever the source of truth of what an insurance claim really is probably an adjuster.
Yeah, no, that's a really interesting idea. And actually never thought of that. I like that idea. My only concern with trying it is the token counts that I would run into, which is why I like TF-IDF, yeah. Like, I can run things through one time and then never have to do it again.
As a follow-up to that, if you ever do, I'd be very interested to know the performance differences, because my assumption here is that your version would be significantly faster. Like, I'm guessing it gives answers almost instantly.
Sub-second, yeah.
Yeah, then whereas like an LLM, you're going to be waiting maybe 5 seconds for it to ingest your input and give you some kind of classification on the other side.
Yep, and now if you want to get really advanced, you take your dictionary and you apply a hash to each word so that you have instant lookup on the words. It doesn't have to search through the dictionary to find it, which is how search engines do it.
On the topic of search engines, is there an amount of data that makes it untenable or too much information for it to be accurate? Or does it continue to get better the more data you have? Is there a sweet spot? Like if you're classifying the Bible versus classifying red shoe, blue shoe.
No, I'm following you. I'm trying to think if I've got a decent answer to that question. I think it depends on contradictions, honestly. How often do the descriptions contradict other things? I think is going to be the biggest limitation. So for example, like my Apple example I showed you earlier, if you start running into a lot of things like that, it'll blow up your TF-IDF where it just starts becoming useless because it doesn't understand that context, it doesn't understand that you're asking about this concept. It does not handle that.
So, I've got two questions. This just made me think of. Number one, you've talked a little bit about data normalization going in to deal with like ran versus run. Do you ever do the inverse, where you take Apple and expand it with an LLM with the additional context to Apple computers, as like with a dash in there or something like that, to spread apart the uniformity there?
That's a really clever idea. That's totally doable.
Do I get a check in the mail now?
I'll nominate you for the Excellence in Technology Awards. So you could do that with your thesaurus, where you could just, yeah, but no. Yeah, but no. If you use an LLM, it could do that.
Or a human classifier.
If you've got a human classifier to do it, but otherwise TF-IDF is going to look at it as like, I don't know which one that is.
Well, if you separate it, like if Apple became Apple-computer, still one word.
Yeah.
Like now it's really clear to TF-IDF that they're
Yes.
really just separate things, and it wouldn't start putting them in the same bucket.
Yeah, and in that same vein, the opposite is also true, where you see people hyphenate words one time, and then not hyphenate it the next time. Those become two different terms in your dictionary,
It all depends on the context.
It does, it really does.
The second question is certainly like just a more mechanical one. Like when you're doing stuff with TF-IDF, what kind of tools are you using? Are there libraries to help train some of these? Like what are you reaching for?
Probably, I just scripted it all in pandas.
Nice. Okay.
Google says scikit.
Oh, scikit learning. Has some
Another tool that I found to be super helpful is Fuzzy Wuzzy. Fuzzy Wuzzy will do a token similarity match across terms, and you can even have it search across terms without respect to token order to find similarity. Fuzzy Wuzzy is pretty handy.
Any other questions? Going once, twice.
And we have one in the back.
Oh, one more in the back. Okay.
This is more of a comment, but as someone that also lives in XML, I just wanted to say I appreciate your end slide.
All right, please give him a huge round of applause.